If you're going through these nuggets in order, which I do highly recommend, then at this point, your taste buds are probably salivating for some configuration, because you're coming out of two heavy nuggets of concepts of OSPF. And rightly so. There's a lot to OSPF, but from here on out, we're turning the configuration corner, as in everything as it relates to OSPF will be done in a configuration-centric sort of way. There are more concepts to learn, definitely, but we're going to do it as we configure it and talk about it and discuss it as we go. So this nugget is going to be dedicated to implementing not so basic OSPF. In that, we're going to talk about, of course, the basic core implementation, a lot from CCNA, so it'll act as a good review from there. But then we're going to step it up rather quickly into route summarization, multi-area environments, influencing DR election, and then adjusting the OSPF cost calculation. We're going to do it all in a GNS3 lab format. So here's the landscape that we're going to be working with as we get into the OSPF configuration. You can see why I said it's a not so basic OSPF configuration, because right off the bat, we're in a multi-area environment. You see area 0 right here. This is going to be our backbone. All routers must connect to that, or all areas must connect to that, I should say. Then over here we have area 10 and then area 20, little 500 kilobit per second link, bunch of loopbacks over here to simulate a larger network than we really have, and then over here on router 1 I have a bunch of static routes. What are those for? Well, that's what this lab is going to be all about. So you can see, let's work through this lab. Again, if you want to give it a whirl on your own before we walk through it, you are more than welcome to do that. I would actually encourage you to do that. Find your weak spots and then come here for the solution. But I am going to walk through this entire lab, explaining everything as I go. Up front, we see the lab diagram right here, and then we come drop down. We've got our objectives. Number 1, configure OSPF for the above network diagram. Router 1 will act as an ASBR, so this guy's connecting to our external networks over here, by redistributing a series of static routes into the OSPF network. So that's how we're going to simulate an ASBR without me having to set up a whole nother network topology over here running EIGRP or something like that. It would be easy to do, but by golly, even easier than redistributing some static routes. So we're going to send these static routes, which all point to null 0, and that's fine, into the network. These routes should not increment their metrics as they pass through the network and should have an initial OSPF cost of 200. Now we're starting to deal with the different types of OSPF routes here, which is the E1, E2. We'll talk about that again in a moment. All routers should have a router ID reflecting their host name. You should be able to ping this router ID throughout the entire OSPF network. Okay, so that's definitely enough to chew on right there. Let's work through that, going router by router. Now, as we go through the future OSPF nuggets, I'm planning on pausing it as I go through a lot of the basic OSPF configuration, but I'm going to do it all right here, just to make sure everybody's on the same page with what's going on. So let me slide router 1 into the picture. We've got router 1 ready to go. Hit enter a couple times. I've already gone through and configured all the physical interfaces. You can see there's not too much to router 1. We just have fast Ethernet 0. I do want to do a show run and include static on that, because I'm thinking my ASA. I really meant include IP route. So I'm going to have my IP route here with all these routes to null 0. That's going to be my external routes. So let's get OSPF running. I'm going to do a show IP protocols just to prove there is no routing protocol running right now. I'll do router OSPF 1. Now, there was no restrictions in the lab, correct me if I'm wrong, about how I put these networks in here. So it should be very simple. You know, I don't have to use specific wildcard masks or anything like that. I'm going to go under router 1. I'm going to type in network, and we'll do 172.30.0.1. 0000. Easiest way to put a network into there. We've got the network running. I'm also going to follow up on this statement at the end. It says all routers should have a router ID reflecting their host name. Should be able to ping that router ID throughout the network. Now, typically, you should do that command first, router ID 1.1.1.1. And the reason I say that is because as soon as the router forms a neighbor relationship, the router ID is fixed. Meaning, if I type this command in after some neighbor relationships have already formed, the router will say, nope, sorry, I've already chosen my router ID, or already chosen my router ID. It is 172.30.0.1. You can't change this without clearing the whole OSPF process. I'll show that to you in just a moment, but that should be good for now. But I'm also while I'm here, going to do this redistribution. Now, this is definitely something I did not talk about fully in the basic concept nuggets we just mentioned a moment ago, because redistribution is truly a part of a section later on in the series where we're integrating multiple routing protocols. But let me just work through this with you. Redistributing a series of static routes, here they are. The command is simple enough. I'm going to type in redistribute static and hit a question mark. Now, first and foremost, I'm going to add this subnets keyword. And the reason why is, by default, OSPF will try to summarize. That is, these are Class B networks. It would try to summarize that back to its default Class B boundary if I didn't type in subnets. I want all the specific subnets, so we'll add that in there. I'll hit a question mark again. You can see I can type in metric and metric type. Now, the metric, the lab did clearly state that the routes should not increment their metric, but they should start off with an initial OSPF cost, or metric, of 200. So I'm going to go in here and say the metric should be 200. So as they come in, it's gonna end up with that metric. And then now we come back to the second statement. It said these routers should not increment. These routes should not increment their metric. Now we're into. Hang on, let me grab my little pad and pen here. Now we're into the different types of OSPF external routes. When OSPF advertises external routes in, it can mark them as one of two types: type E1 and type E2. For some reason, for me, this has always been the hardest thing for me to remember, and I've never come up with a great, here's a great analogy or something like that that can tie it in my head. I have to admit, it's been brutal root memorization for me. By default, or let me, before I even talk about defaults, type E1 routes increment their metric. What that means is I sent them in with a default metric of what? 200, right? We specified that. So all these routes are coming in from router 1 saying, hey, I've got a connection to all these networks, and that costs me 200 to get there. So this is going to fly across the rest of the network to all these other routers, and they're going to get it and say, oh, okay, well, if it's 200 for you to get there, and maybe it's a cost of what? We'll say 10 for me to cross this network to get to you, then it's going to be a cost of 210 to get to me. And as it continues on, these routes will go throughout the rest of the network, right? These guys will say, okay, well, it costs, whatever, 1,000, if you will, to cross this 500 kilobit per second link, plus the 210, plus, et cetera, et cetera. So you end up with this total metric by the time it's said and done. That would be if they were type E1 routes. As in, they are increasing their metric as they go throughout the network. Now, if there's only one exit point, then a lot of times you might choose E2, where it does not increase the metric. And now we're back to what the lab was saying. These routes should not increment their metric as they pass through the network and should have an initial cost of 200. Type E2 says they came in as 200, and as they arrive at you, they're 200. As they arrive at you, they're 200, and so on. Now, what is the reason for doing that? That saves a couple processor cycles in the end, but the big picture is there's only one exit point from this network, router 1. Router 1's the only one that has a connection to these external routes, so what's the big deal? I mean, if you only can go one way to get there, then why do all the math to increment the metric all the way through? Now, it would be a different story if we had router 9 over here, we'll say, that also had connections to these external networks. Then I would want type E1, because some routers might have a better route through router 1, other routers might have a better route through router 2, and if you use type E2, nobody can tell the difference. They would just say, well, it's all equal to me. So, one other thing I'll mention, the default is a type E2. So E2 routes are if I don't type in some other type, then it will be E2. But just for grins, I never like accepting defaults. Where's my secure CRT? There we go. I'm going to type in metric type 2. And you can see there's our external type 2. I hit question mark, and you can see we can get into some more advanced stuff, and believe me, we will when we get into the advanced redistribution. But for now, I'm just going to hit enter, and now we're sending those static routes in. But the question is, we're sending them in to who? Nobody right now, because we haven't configured R2 or R3. Let's do it. I'm going to go to router 2. Do a show IP interface brief, always my first command on any routers, just to get the landscape of what's going on. And sure enough, just like I'd expect to see, I see one serial interface over here on the 172.30.10 network and one Ethernet on the 172.30.0 network. So let's configure it. I'm going to go into router OSPF 1. Configure, and now I'm going to do it out of order because I want to show you. I'm going to do network 172.30.02.0.0.0 area 0. Now it's going to form a neighbor relationship because it's connected to the same switch. It should form a neighbor relationship. Hang on. Okay, I was just impatient. There it goes. We've got the neighbor that has now formed 1.1.1. I'm going to do a show IP OSPF neighbor. Great command. And I can see right up front, this guy has become the DR. Now, it's going to be a question later on in this lab, but for now, let's go with it. You can see he's the DR, but let's flip over to router 1. On router 1, notice, show IP OSPF neighbor, it's formed a neighbor relationship with this guy, the BDR. Now, this is not the right router ID. It said in the lab clearly that all routers should have a router ID reflecting their host name. Now, I chose 2.2.2.2, 1.1.1.1, and that's fine. A real exam environment would definitely be more specific because this is a very vague statement. I could say, well, my router ID is 172.30.1.2, which reflects the host name, or because we have router 2. But for now, I'm just going with it. I'm going to go in and go router OSPF 1, router ID 2.2.2.2. Watch what happens. Wham. It comes up and says reload. Yeah, that's not a devastating event. Or clear the OSPF process. Also equally devastating because, well, not equally, but almost as equally, because it's going to take down the whole OSPF routing process for an instant. That's because we've formed a neighbor relationship with the router ID. Now, this will be the new router ID, but it won't take effect until I do this. Oh, I'm going too fast for my own good. Yes, I would like to clear the OSPF process. So now, tears down the neighbor relationships, resets the whole thing, and when it comes back up, router 2 would indeed be seen as 2.2.2.2 as the router ID. Okay, so from here on out, I'm going to configure that first. But now I want to add in the other network, which was network 172.30.10.2.0.0.0 area, and we are putting that guy in area 10. It's going to be going between router 2 and router 5. Good so far? So what we've got now is we've got two of the 5 routers configured. Router 1 being our ASBR, redistributing those external routes. Router 2 being an ABR, simply because it has 2 interfaces in multiple areas. Let's see if those neighbors, yeah, indeed, the neighbors have come back up. They're running a little slow today. You can see over here, notice we see neighbor 2.2.2 now over on router 1. You guys follow? So now I'm going to just do a show IP route on router 1, and I see the inter-area route, meaning the route that is connecting to another area. And that one's coming from router 2, simply because its serial interface on router 2 is in area 10, another area than area 0. Also on router 2, flip over there, do a show IP route. What should I expect to see? External routes. Type E2 routes coming in here. You see 172.16.0, 123. You also see them all flagged with a cost of 200, and that will never increment as it goes throughout the network. Why? Because it's an E2 route. If I would change that to a type E1, you would see a cost of 200 plus whatever the cost is to get from router 2 to router 1. So good. Now we can start moving a little faster as we go through these routers. You've got the basics down. Router 3. Let's go in. Global config, router OSPF 1. I'm going to start off with the command router ID 3333. Network 1. I skipped it. And I always need that one. Network Ethernet is connecting to my backbone area 0. Network serial right there is connected to my area 20. That's going to be our link between router 3 and router 4. 20. You see those neighbor relationships form. That should give you a warm, fuzzy feeling. Do a show IP route. I should see all my external routes and the inter-area route coming from router 2. You can see that's coming from him. We've got a cost of 210 to get there because we're going across the Ethernet network. It's good. So good. We're good with router 3. Jump over to router 4. Router 4 is fully in area 20. So let's do it. Show IP interface brief, config T. Oh, and we've got these loopbacks as well. So I'm going to do router OSPF 1, router ID 4444, network. Let's get easy on these guys. 10.0.0.0, area 20. That's all area 20 routes, and network 172.30.24.0.0.0, area 20 as well. So that should bring up the neighbor, good, the neighbor relationship right there to router 3. Do a show IP route, and we should start, okay, we're not seeing anything. That's good. So let me do a show IP route again. There, it's even better. Just took a little while for the SPF process to run. I'm seeing all the E2 routes, our external routes. I'm seeing all the inter-area routes I would expect to see. That's good. This is the guy coming from area 0. This one's coming from area 10. Likewise, I should be able to go now to, let's just jump over to router, well, let's go router 1. Let's go all the way. Do a show IP route. I notice router 1's routing table is getting a little bigger. We're seeing all these inter-area routes coming from router 4 over there, all those loopback interfaces. Good. So we're humming along. Let's go to router 5. Do a show IP interface brief. Again, identifying router 5, sitting up here, there's all his loopback interfaces. And we've got all interfaces in area 10. So let's do it. Router OSPF 1. Router ID 5555. Network 10. Let's go 10.0.0.0.0.255.255. Is there any consistency with my network statements? No. Network 172.30.10.5. That's consistent. Area 10. There we go. That should bring up the OSPF relationships. Good. So now let's just give ourselves that warm fuzzy feeling. Show IP OSPF database. This should show us everything, and you can see these are the different LSA. Actually, have I talked about this? No, I haven't. We will talk about this command much more later when we get into all the LSA types that are there. Yes, when we get into the special areas, we'll definitely talk about this. But I can see type 1 LSAs, these are the router ones coming from within my areas. I see the summary networks coming in from area into area 10. These are all the links that are being advertised from the other areas. I also see summary link states between them. These are type 5 LSAs. I typed that command too early. We'll talk about that command when we get into the multiple areas. I meant to do a show IP route just to give us that feeling. Now, one thing you'll notice with OSPF, all of these loopback interfaces are actually advertised as loopbacks. You can see with a /32. Now, interesting thing is this is done. Let me do show IP interface brief. I'm going to do a show run interface loopback 1. And you can see when I configured this loopback interface, I actually gave it a class C subnet mask. But OSPF said, no, 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 you're not fooling me. I know that that's a loopback, and I'm advertising that as a /32 subnet. And you can see over here on router 1, it's learning about all of these loopback interfaces with a /32 subnet. Now, I will tell you, for sake of lab environments, you can actually tweak that behavior. If I go over to, let's go to router 5. Well, yeah, let's go router 5. And I go under interface loopback 1 and type in IP OSPF network. I'm changing the network type to point-to-point. We'll see a lot more of this command when we get into non-broadcast multi-access networks like frame relay. More on that later. But what that does is kind of trick OSPF to where OSPF will say, oh, okay, so that's not a loopback. That's a real network. So from there on out, it will actually advertise. I'm not too sure if I'll have to clear the process. Oh, trying to do a Control-Shift-6X or not. I don't know. Let's find out. Okay, good. Look, take a look at this. Didn't have to clear the process, and now it's actually advertising that one loopback as a /24 because it's when I went in there into that interface and typed in under loopback 1 IP OSPF network point to point, OSPF said, oh, well, excuse me, I must have been wrong. I thought it was a loopback, but really that must be a point-to-point network, so I'll advertise the real subnet. So if you're in a lab environment and you're seeing a bunch of these and you're like, I don't like those, I want it to look like real networks, you can do that using the IP-OSPF network command. Sweet. Okay. Step 1, I think we are done. Let's just verify. ASBR is redistributing. Default metric is set on those routes. E2 as the metric type. Router ID, good. So it says, after completing this initial step of the lab, one of the routers in area 0 will become the DR, and one will become the BDR for the Ethernet segment. Which router will become the DR and BDR? So I guess here's the big question on this statement. When a DR and BDR is elected, they're going to stay that way, even if a better DR and BDR comes online. Matter of fact, let me go back here and show you. I'm going to do a show IP OSPF interface on router 1. And you can see this shows router 1 is running OSPF on Fast Ethernet 0. It's a broadcast network, but look at this. State is DR, meaning I am the DR for this network. Now, here's the catch. That happened by default, and you can see right here it's formed an adjacency with 2222 as the backup designated router. I'm going to do a clear IP OSPF process, which will reset all OSPF processes on router 1. The reason I'm doing that is because router 1 is the DR because we just configured it first, and it said, well, I'm the only one here, so I'm the DR. Router 2 came online simply because it was configured second, and it became the BDR, and router 3 became the nothing because it was just happened to be configured third. Now, this statement is kind of tricky because we just walked through the complete initial configuration. It says after configuring the initial step, one of the routers will become the DR and one will become the BDR. Which one is it? I would say that guy became the DR and router 2 became the BDR simply because they were configured first. But let's hop back to Secure CRT here. We've reformed our neighbor relationships. I'm going to do a show IP OSPF interface. Look at what's happened here. Router 1 came online, same network type, but it became a state of druther, meaning you are neither the DR nor the BDR. You're a DR other. And if I go to router 2 and look at it from router 2's perspective, do a show IP OSPF neighbor, sure enough, it sees router 1 as druther. It sees this guy as the BDR, and router 2, if we looked at router 1's output, router 2 is indeed the backup as the designated router. Now, if I were to clear everything again, if I were to go to router 2 and do a clear IP OSPF process, wipe the whole thing, kind of bounce all those relationships, all those are going to go down, all of them are going to come back up. Now what's going to happen? Well, this whole designation is going to go away. Oh. Working with Word is fun sometimes. So router 1 will no longer be the DR at all. Router 2 will become the BDR, and router 3 will become the DR. Now what's going on? Is it just kind of whoever comes latest? No, what's happening is the natural state of OSPF is taking over. Remember, by default with OSPF, grab my pen here. By default with OSPF, the one with the higher OSPF priority becomes the BDR and the DR. Now by default, as we saw in Secure CRT when I was looking at this, you can see by default everybody has a priority of 1. That means everybody is considered essentially equal to become the BDR and the DR. So what's it used to break the tie? Well, let's look. Show IP OSPF neighbor. Now I see 3.3.3.3 is the DR, and, well, okay, 2.2.2.2 is druther, simply because 2.2.2.2 router 2 was down, and router 1 happened to be up, so it decided I will become the BDR. Okay, but again, if I cleared router 1, router 2 would become the BDR. Essentially, all of them are coming up with an OSPF priority of 1. They're all tied. So it's using the higher router ID to break the tie. Router 3 has the highest router ID, so it should always become the DR. Router 2 has the next one, so it will always become the BDR. Now, router 1 happens to be the BDR right now. Why? Simply because router 2 was down. We cleared the OSPF process. Router 1 said, well, router 2's down, I'll become the BDR, and there is no preemption. Meaning, once you elect a DR and a BDR, you can't preempt it without clearing the OSPF process. So, let's come back to the lab, and again, this is an arguable point for the exam, but I would say if you are in an exam environment and you got a question like this and they said, okay, everything is configured and everything is running, who is the DR and who is the BDR? Without batting an eye, I would say router 3 is the DR, router 2, oh no, pretty arrow, router 2 is the BDR, because those have the higher router IDs. That's the default. So I would write next to these guys, router 3 is the DR and router 2 is the BDR. Any other criteria that I would see in the output would simply because I configured router 1 first or something like that. Does that all make sense? So that's how the default state of affairs are. But let's look at this. It says, no, forget all that and make sure R1 becomes the DR on the Ethernet segment. R2 and R3 should not become a DR or a BDR for the Ethernet segment in area 0. It says after a change is made, what type of neighbor relationship should exist between R1 and R2? How about R2 and R3? Wow, a lot in that one statement. So let's take it piece by piece. I'm going to first off ensure R1 becomes the DR on the Ethernet segment between R2 and R3 at all times. That can be accomplished using the IP OSPF priority command. Let me show you. Bring it back up here to router 1. You notice that router 1 has fast Ethernet 0/0 attached to this segment, this shared segment between these guys. So I'm going to go into router 1, into fast Ethernet 0/0, and type in IP OSPF priority, and then type in a number. Now, here's the key. Everybody is 1 right now. Anything higher than 1 will beat the others and become the OSPF DR for the segment. I'll go ahead and use 200 because it's a nice round number. Now there's also a key right here, and it goes with the rest of this. That will ensure router 1 becomes the DR on the Ethernet segment, but R2 and R3 should not become a DR or BDR for the Ethernet segment. The way that we accomplish that is by shooting into R2 and R3 and setting their priority to 0 for that segment. Now again, why are we doing this? Because the lab told us to. Why else? You wouldn't normally do this for a shared Ethernet segment. You typically would want at least a BDR playing in the game. So we're going into fast Ethernet 0/0 and typing IP OSPF priority 0. And this is on router 2. Let's also drop over here to router 3. Same thing. Global config mode, interface fast Ethernet 0/0, IP OSPF priority 0. And okay, not really. This does come in very useful. However, it's typically done in NBMA networks. Again, non-broadcast multi-access. We'll talk about those more later. Now, as of right now, we've probably changed nothing. Let's go back and do a show IP OSPF interface. And surely we are the DR. Hang on. Let me do a show IP OSPF neighbor. Hey, that's interesting. Now, I learned something new. I thought I would have to clear the IP OSPF process before that would take over, but it looks like, in this case, the DR is immediate. And look, take a look here. This guy is now DR other, DR other. So you can see right now that this router 1 is the only DR in the segment. By setting the priority to 0, they have now revoked their BDR capabilities. So router 1 is the only DR on the segment. So let's go back to the question. It says, okay, they should not become the BDR and DR. Okay, so after this change is made, what type of neighbor relationship should exist between R1 and R2? We'll look up here. And think of the different neighbor states. You remember when we went through that in the concepts, the down, two-way, X-start, exchange, all those different ones. Well, router 1 and router 2, as a matter of fact, we can see it right here. We just saw it. They are full neighbors. And same thing between router 1 and router 3. They're also full neighbors. Like they are fully exchanging routes. So with that being said, let's look at the rest of the question, the rest of the story. It says, okay, what about the relationship between R2 and R3? R2 and R3. Think about that. So we've got R2, which is a full neighbor of R1. R3 is a full neighbor of R1 because R1 is the DR. Now you might remember back to the concepts and think about, well, what about the non-DR or BDR routers? What kind of relationships do they form? Well, it should be, the answer, drumroll please, is two-way. a two-way relationship. You might remember that when the routers first exchange hellos, they are down. As soon as they realize they are compatible with each other, they go into two-way. However, on a shared Ethernet segment, that's where they'll stop. They'll say, well, wait a sec, you're not the DR, you're not the BDR, so I'm done talking to you. Yes, I know that you exist, you're a good friend of mine, but we are not going to exchange routes because we do all of our exchanging through the DR, through 224.0.0.6, and he will send all the updates back to us on 224.0.0.5. So let's verify and make sure that our hypothesis is true. Over here on router 2, do a show IP OSPF neighbor. Take a look at that. Right up front, it shows neighbor 200 priority full designated router. Look at this guy. Here's router 3, two-way relationship, druther. So do you see how all this plays out? And you also see, we haven't even talked about it, but notice the relationship between R3 and R4. Well, wait a sec. We're on, R2 and R5. How's that? R2 and R5, we've got a point-to-point link between them. Look at this, 5555. Relationship is full, and he's a nothing. Because on the point-to-point links, there is no DR, BDR. They just send everything to 224.0.0.5 multicast address because it's point-to-point. There's no use in only allowing some updates to go to some people and so on. So that's the idea. That's I would say a huge learning concept right there of not only how the DR and BDR elections work, non-preemptive to where the first one configured becomes the DR and so on, but also seeing the relationships and how they form after you've elected the DR and so on. So let's move on to the last three objectives. Implement summarization at the ABRs in the network to make sure the routing tables throughout the network to make the routing tables throughout the network as efficient as possible. Okay, so let's jump back over here. What we're looking at is, again, focusing in on router 2 and router 3. These are, as we've already discussed, the ABRs in the network. These are your summarization points. Likewise, R1 is an ASBR, the only other summarization point that you have in the OSPF network. One of the beauties of EIGRP is you can go anywhere, any router in the network, and summarize just by going into the interface config mode. OSPF, not as flexible. You only have these specific routers. So what we're receiving is router 5 is sending all these routes. He can't summarize because he's not an ABR, he's not an ASBR. So he's sending all these loopback interfaces to router 2. So let's shoot over to router 2 and see the whole story here. Doing a show IP route, and there's all our 10.10 networks. These are all coming from router 5 over here, these loopback interfaces. So I need to summarize those as I go into area 0. The command that we're going to use to do that is area, and I'll just put X, range, and then our summary address. So in this case, we're going to go into the ABR and say area 10, range, and then whatever our summary address will be that encompasses all those. Now again, I'll show you my method of summarization. I always think in terms of increments. 128, 64, 32, 16, 8, 4, 2, 1. There's many different ways to do summarization. Some people break these into binaries, find out where the differences are, draw their lines, all that kind of stuff, and that works, but it's just a lot easier. Once you get used to seeing binary all the time and seeing the increments, it's just a lot easier to say, okay, what increment will catch all these guys? Obviously 128, 64, they all will, but the smallest increment that would catch them all is a 4. So if I were to go 10.10, whoop, that's a funky one, 10.10.0.0, then go 10.10.4.0, 8.0, and so on, that would definitely encompass all these guys. 0, 1, 2, 3. That would be this first range, 10.10.0.0 through 10.10.3.255. Sorry, my handwriting's getting smushed there. But that would be the perfect summary address. So then I would think, okay, how many ones do I have to go over in the third octet? There's our third octet right there, to get to the number 4. 1, 2, 3, 4, 5, 6. Okay, great. So if I was looking in binary, all 8 bits are the same here because they all start with 10, right? All 8 bits are the same here because they all have the second octet of 10. In the third octet right here, I have to go 6 bits or 6 common bits to get to that increment of 4. So that will give me a /20. Voila. So just like that, 10.10.0.0 /20 is the summary mask that would encompass all, whoop, not this guy, all of these loopback addresses over here on router 5. Now again, that's my quick flyby way of doing summarization. If you like counting the binary numbers, and for instance, and I'll just show you if you haven't seen this before, you can say, okay, third octet 0. 0 is all zeros in binary. 1 is 0 0 0 0 0 0 0 1. 2 is 0 0 0 0 0. You see how this works, right? And then I go, okay, 0 0 0 0 0 0. This is 3. So you look and you go, okay, well, it looks like they all have the first 6 bits in common. The changes happen over here in the 7th and 8th bit. So again, you would arrive at that same conclusion. You would say, okay, then we need to go 6 bits in the third octet, or /20, or if you were going in decimal, it'd be .252. All those facts together. So whatever way you feel most comfortable, great. It's just if you got a lot of addresses, doing this, it just eats up some time. So all that being said, let's make magic happen. I'm going to go on my router 2, global config, router OSPF 1, and I'm going to type in area 10. Hang on, we're at area 10, right? Area 10 range, and then you can see it saying, well, what summary address or what IP address to match. And I'll say 10.10.0.0 is my quote-unquote summary address with a mask of 255.255.252.0. Someday, Cisco will allow us to use slash or cider notation for that, but for now we have to type in decimal. That's the decimal summary mask. So wham, immediately, as soon as I do that, router 2 says, let me clear all this off. Router 2 says, I will take all of the individual addresses that match that summary mask from area 10 and suppress them and only advertise the summary route out to area 0. So let's see, let's make sure it's working. Shoot over to router 1. I'm going to go show IP route, or route, and right there is our summary mask. Sweet! 10.10.0.0/22. It looks beautiful. Notice all of the .10.10 networks are suppressed, and you can see down here all that's left is the 10.20s, and those nice easy summary there, right? Those are going to be the same thing, right? 10.20.0.0 with a /22 mask, or 255.255.252.0. That'll catch all those guys for area 20. So let's head over to router 3, make it happen. Router OSPF 1, area 20, range 10.20.0.0 with a mask 255.255.252.0. You can keep it along. If I'm going too fast, pause me. And so wait a second, I have to hit the enter key. So that will be the summary mask that encompasses all those. Again, same thing that we saw up here in area 10. So let's verify it. Shoot up here to router 1. Show IP route 10.10, 10.20. Good. We've now suppressed all of those. And we've summarized them. The last piece, so that was implementing summarization and the ABRs to make the routing tables throughout the network as efficient as possible. Now we'll drop down here and we'll implement summarization at the ASBR. The summary route should have the same attributes as the original individual routes redistributed into the network. So what does that mean? It means that do the summarization at the ASBR, but that summary route, it's going to encompass all those in one route, and that one route should have all the same attributes, like the same cost. It should be the type E2, you remember that? All those same attributes as the original individual routes. So let's head over here to router 1. This is going to be a little different. Remember, ABRs and ASBRs are where summarization happens, but ABRs have the luxury of saying area such and such, range, blah, blah, blah. Well, when you come to an ASBR, this isn't an area. I mean, this could be, and it typically is, like a RIP network or an EIGRP network or some other type of BGP. It's some other type of network that we're redistributing, and all of these have no areas. There's no concept of area. So you have to go to router 1 and you have to say, okay, R1, summarize, but it's not area such and such range. It's going to be summary address such and such, and just inject that into the network. So likewise, the good thing I picked these same routes, right? So we don't have to keep doing summarization. It's the same mask as these guys, 255.255.252.0 or /22. So let's head up here to router 1. go into global config, router OSPF1, and I'll just type in summary address. This is the command, summary address. And then what summary address do you want to use? Well, I'll come back here and say it is going to be 172.16.00. And the summary mask will do 255.255.252.0. And I'll hit question mark. And notice it says we've got a couple tags. The do not advertise tag mentions type 7 LSAs. We'll get into all those, but that's it. I mean, for this, that's all we have to do. We'll get into these when we get into the special area types. Hit enter, and now it's summarizing all those addresses. So let's verify. Let's head over to router 2, show IP route, hit enter, and yes, there it is. You can see we've got 172.16.00/22, type E2 200. And you might be thinking, well, okay, so what did you do so the summary route would have the attributes as the individual route? It does that by itself. It actually will inherit the attributes of the individual routes that you're redistributing into the network and take those on. So obviously, if you didn't know that, then you'd be looking for what syntax can I use, but really it just does that by default. Good. So where are we? We now have all the tasks completed. We've got summarization happen. The last thing that we need to do is drop down here to task 5. Says the organization plans to upgrade to gigabit Ethernet in the coming months. OSPF should accurately calculate its metric, assuming gigabit Ethernet will be the fastest link in the network. Now this objective goes back to 1982 when OSPF was released, and people, think about 1982. I mean, we're talking the B-52s, the BGs. You know, if you were to throw gigabit Ethernet out there, people would be like, yeah, that's like Star Trek, right? Star Wars technology. We'll never be at gigabit Ethernet. I mean, you've got your, we're still at 300 baud modems back in 1982. So gigabit Ethernet was pie in the sky. You're never going to get there. But now it's a reality. So the problem is OSPF's cost formula says I'm going to figure out the cost by 100 divided by the bandwidth of the link in megabits per second. Okay, so for instance, if this is a 100 megabit per second link here, then the cost would be 100 divided by 100 megabits per second, and that would equal 1. This is a 500 kilobits per second link, so the cost would actually be 100 divided by 0.5 megabits per second, because, again, it's half a megabit per second, and that would end up equaling 200 or so, correct? Yes, that's right math. So this is a problem when you have gigabit Ethernet, because you can't have fractions of metrics in OSPF. So if I had 100 divided by 1,000, we'd still end up at a cost of 1. You throw 10 gigabit Ethernet or 100 gigabit Ethernet out there, and you're going to have a cost that is also equal to 1. So OSPF cannot accurately distinguish between the different high-speed links above 100 megabits per second until you adjust what's called the auto cost reference bandwidth. The way that we do that is we go into each router. Now, this is one that you have to do on every single router, or else you're going to get very inaccurate cost calculations throughout the network. You go under router OSPF mode, which is exactly where I was, and type in auto cost reference bandwidth followed by a number. Now, be careful. You might be tempted to think, okay, well, gigabit Ethernet, sure, let's put 1,000 in there. But then you might think, oh, well, yeah, we're upgrading this right now on all our routers because gigabit Ethernet's the fastest we have. But what about when 10 gig or 100 gig? And you might just say, well, good grief, why not just make this, something insane without exceeding the valid range that you have up here? Will that work? Yes, but there's a big caveat in doing that and making it, what is that, a million? Making it a million megabits per second. The problem is that, the fast links, 100 megabits per second, are still going to generate a very large number. But when you start getting to these speed links, or if you've got 128K links or 64K links somewhere scattered in the network, those links immediately go down, because there is a maximum metric that OSPF has. I don't know what it is off the top of my head. I think it's like 4 billion something or a million something. I'm not too sure what it is. But that is considered the infinite metric, meaning that metric is used when OSPF wants to mark a route is down. So the problem is if you adjust your auto cost reference bandwidth super high, then your really slow links, good grief, I got a little circle there. Your really slow links, like your 0.064 megabits per second or whatever super slow links, are going to generate a number so big that OSPF will say, oh, that must be an infinite metric. It's unreachable, so I will not advertise that network anymore. So what I would suggest is just make it big enough for your fastest link, or maybe just go maybe a year beyond. Like you're at a gig now and maybe you plan on 10 gigs, so you do something like that. But of course our lab objective said to make it a gig, so we changed that. It says please ensure it's accurate across all routers. So this would be something that we would go in on router 2, router OSPF 1, and I won't make you watch me do this on all of them. Let me flip back through the rest. There we go. And so now I've gone through all 5 routers. You can see I'm over here on router 5, got the auto cost reference bandwidth put into place. Now let's just glance up here. You can see that originally these inter-area routes, and this is before we did summarization, but originally these guys were like a cost of this and so on. Let's do a show IP route now. And now you can see it's readjusted all the metric values to become accurate based on the new formula that we're doing. Instead of dividing it into 100, we're dividing it into 1,000. You can see right up front the metrics immediately reflect that, to where no longer are we at 411, we're at 4101. The only one that did not change is this guy, simply because he was marked as an E2 type route, where his metric was set at the beginning and does not change throughout the rest of the network. Sweet. Ladies, gentlemen, we have completed the OSPF core configuration. So what I would recommend you do, yes, if you just watch this, kind of going through, getting familiar with it and understanding it, great. Go ahead and pack this one away until the end of the series. And when you're going back and doing your studies, run through this lab yourself. Try it out, in GNS3 or whatever lab environment you're having, to make sure that you have this solidified in your mind and you're able to do all of these concepts. Good deal. So what we have done as we've gone through this section is looked at all of the core OSPF configuration, talking about OSPF network commands. We saw a little review on the wildcard mask and what to set that to. Areas, we set up ABRs, we set up an ASBR. We implemented route summarization at the ASBR and the ABRs to make it more efficient. We influenced the DR election. We saw what it was by default. We then went through and influenced it using the IP OSPF priority command. And then finally, we just adjusted the cost calculation using the auto cost reference bandwidth. So at this point, we have a pretty sweet network humming along running OSPF. From here on out, from beyond, I'll say beyond this nugget, we're going to get into all of the specialty things with OSPF, such as the different area types, the different LSA types, all of the ways that you can tweak it, and especially, this one's going to be a doozy, when you get into the NBMA networks, non-broadcast multi-access, a lot of funky things happening there. But for now, I hope this has been informative for you, and I'd like to thank you for viewing.